you might need to replicate the test. In Lesson 9, we explore deploying a test sequence. After you have developed and tested the necessary pieces of a test system, you might need to replicate the test system on multiple test machines on the test floor. In this lesson, we'll explore methods for deploying a test sequence to the production floor based on your system needs. To ensure that you have a successful deployment, you must first locate all of the files that are needed to be deployed to the destination computer. In this section, we'll identify the components that are required for a complete test system deployment. A Teststand test system relies on a variety of files and types. To distribute a Teststand system successfully from one computer to another, you must be able to identify, collect, and deploy all the components of a Teststand test system to the correct locations on the target computer. While there are many different items to consider, we'll focus on the following: deploying the Teststand runtime and other appropriate runtime engines, distributing test code and including files that are called dynamically, and also distributing a user interface. Refer to the Identifying Components to Deploy topic in the NI Teststand Help for a more detailed list of components to consider including in a deployment. Engine is required for any Teststand deployment. The Teststand runtime requires the base deployment license. Runtime engines are required for all code modules. Most software runtime engines do not require any licensing, so things to consider are if you call any LabVIEW, CVI, or Measurement Studio code, you'll be required to include their appropriate runtimes. In this slide, we compare the two deployment licenses for Teststand. In the first column, we have the Teststand base deployment license, and in the second, the debug deployment license. Notice that with both licenses, you're able to run steps interactively and set breakpoints and observe what happens as you test out your deployment, but in order to make any changes to your sequence file, it'll require the debug deployment license. Used in the test system code module. Any hardware drivers used in the test system code modules must be included in the deployment. Hardware drivers include NI-DACMX, NI-IMAC, and NI-Scope. And these drivers all include a smaller runtime version that is intended for deployment as well as many other drivers. Another component to consider for deployment is the user interface. You will need a user interface in order to run the sequence files in the deployment machine. The user interfaces provided with Teststand are located in the Teststand public directory underneath the User Interfaces folder. Teststand includes two types, the simple and the full-featured. The simple is targeted to operators only and is known as an operator interface. It's simple and doesn't give the user functionality to edit the sequence file it loads. The other option is a full-featured user interface, which is more intended for the debugging purpose and allows you to edit and debug your test sequence files on the deployment machine. Note that in order to edit sequences or use the development software such as LabVIEW or CVI, you will need a Teststand debug deployment license on the deployment machine. Refer to the Teststand licensing options topic in the NI Teststand Help for more information. The default user interfaces are located in the Teststand public directory underneath the User Interfaces directory. Here we have the full-featured and the simple available, and they can both be used with any Teststand sequence file. We'll open up the LabVIEW Simple UI, and you can see that when we launch it without any sequence file loaded, we don't have the option to run a sequence file or do any executions, as many of those buttons are not available. We'll go ahead and open up the mobile device test sequence file to see an example running in the user interface. Here now the test UUTs and single pass buttons are now available. We can click single pass to run a test execution to see the result outputs within the execution view and the report view. So here it's just like running a sequence file from the Teststand sequence editor, but note that there's no debugging capabilities. This user interface simply runs your sequence files. Once the execution is completed, you can see the report output in the reports view at the bottom and the end of the execution. We can close out the sequence file, but we'll see that the execution is not closed. These two are separate of each other. You can also log out and log back in, and finally use the exit to close down the Teststand operator interface. In the Teststand execution architecture diagram, we can see that the simple user interface fits into the operator interface requirement that we had for user interfaces. This could be the shipping example that we ship, or any customization that you may do in your development. You may want to consider ways to restrict access to Teststand features on a deployment machine. Teststand can limit the functionality itself of the Teststand sequence editor and the user interfaces for certain users through user management. So when you log in immediately, different users can have different privileges. This is designed such that you can limit the permissions of a test operator so that they are allowed to execute sequences but cannot add breakpoints or edit the functionality of a sequence. Why this could be problematic if an operator could change step settings? Well, they could make it very difficult to troubleshoot for technicians and developers if the operators are tinkering with your test sequence. We see without any users logged in, there's no options available. So let's log in the default administrator account to take a look at the user management properties. Navigate to User Manager by going to Station Options and then looking at the User Management tab. You'll note that Teststand has the ability to automatically log in Windows System User, but the user does have to be created in the user management directory before this option can effectively work. We'll see that the user manager file that we're currently using is users.ini in the config directory underneath program data. If we want the option to log in Windows System User, we'll have to create a user in the user manager. So let's go ahead and go to the user manager to take a look at how this can be done. By going to View, then User Manager, we can see the available list of users, as well as the groups that are there. These are all the default ones that Teststand ships with. So let's go ahead and create a new user and name it Tech Operator by right-clicking to insert a user and renaming the user to Tech Operator. So here we can right-click and look at the properties. Let's assign the operator group to the Tech Operator, but we can see that we can apply multiple groups. We have to save in order for these changes to take effect, and let's log the administrator out and log in the Tech Operator. Since the password was left blank, we can just go ahead and choose that option. But we'll see now that the Tech Operator, who belongs to the operator group, does not have options to add a new sequence file or change result processing or do any debugging. The Tech Operator has very limited scope, which is just running the sequence files. Files to include for distributing test code obviously include your sequences, your code modules, any exported limits, configuration files, anything that is required to successfully run your executions for your UUTs. Before you distribute your code, you should complete these 3 tasks. First, use the sequence analyzer to find potential problems with the sequence files. Second, configure the adapters you're using to execute code modules using the runtime engine, or to do it in process. The LabVIEW adapter uses the development system by default, so try changing it to the runtime and see what errors you encounter. Deployed systems typically do not have licenses to run development software, so it is important to ensure that the test system works correctly with runtime software only. Third, ensure that all required files are included, and place all code modules in the same subdirectory of the sequence file that you are deploying. When calling the code module, Teststand will use the path relative to the sequence file to locate your code modules, and ensure that in your step settings you have selected to load from a relative path. As long as you deploy the entire folder containing the sequence files and the code modules, the path will remain valid on any machine. In this activity, you will generate a list of the items in the project that are needed to be deployed. When you're finished, proceed to the next slide to review possible answers. Possible answers for this activity include test sequence files, such as the solar panel test sequence, supporting sequence file, such as the temperature monitor sequence, code modules, simulation driver files, report options configuration, the batch process model, the Teststand runtime, and a user interface that you may want to use on the deployment machine. In this section, we will explore the workspace files and how to use them. Early in the development phase, start organizing your files using a workspace file to be better prepared for deployment. So what is a workspace? A workspace is a file that organizes development files, and it contains references to any number of Teststand projects. This helps keep your project organized, and it's very similar to the structure used by many common development environments. Using a Teststand workspace file also allows integration with source code control to allow you to check out and check in from Teststand. It also stores debugging information such as breakpoints and watch expressions specific for your Teststand files within the workspace. You can use the Teststand deployment utility to create a deployment that contains all the files you specify in a workspace file. When using workspaces, add sequence files, user interfaces, dynamically called files, and configuration files to the appropriate project within the workspace files. Note that you must explicitly add dynamic dependencies in order for TSDU to be able to recognize them for deployment. Otherwise, it is not able to find them since it does not actually run your Teststand sequence files when it analyzes. The Teststand deployment utility can also utilize workspace files to identify and configure the files that you need packaged in your deployment. TSDU, the Teststand deployment utility, automatically detects any dependencies, such as code modules and other files, that the workspace file directly references. For example, if the workspace contains a sequence file, the deployment utility searches the steps in every sequence of the file to find the reference code module and recursively analyzes all files in the workspace hierarchy. The approach that you select for deploying your test system will depend largely on your audience. In this section, we'll discuss 3 approaches to deploying a test system: using a shared network drive, using source code control, or using the Teststand deployment utility. A shared drive deployment architecture concentrates file storage on a shared network drive rather than a local hard drive. There is a master repository that is updated from a shared development drive as developers modify the test code. Once the test code is ready for deployment, you can push it onto a production shared drive, which then can be accessed by all production testers. Consider using this technique with source code control such that you have more visibility and more management over file revisions, file updates, and could potentially have other developers review code. Advantages of this approach include reducing distribution time, ensuring that all testers are using the same test code, and it provides the greatest level of control over distributing test software. This allows your upgrades to be easily installed without having to go through a whole patch or reinstallation process. Caveats do include requiring manual management of files in the deployment, so code modules and sequence file dependencies and configuration files are manually managed rather than having that be automatically detected from something like Teststand deployment utility. Another caveat is common network problems, such as what happens if the network is down. And another caveat to consider is what happens when multiple users are trying to modify the same test code and trying to upload their changes to the network. This is where source code control comes in very handy. You can use source code control to deploy code to test stations within your organization. Using a source code control system ensures that you have the latest versions of the files the test system requires, unlike the deployment utility, which only includes files that were installed on the machine when the deployment was created. In a typical SEC test system deployment architecture, you will have an export folder within your source code control server where you will store your finished edits to your test code and submit any modified modules. Test stations can then synchronize to this export folder to begin using the latest version of your test code. You can submit changes at any time without having to affect the test system because the test station does not receive the changes until requested. Using an SCC system offers the following advantages. Deployment and update tasks scale well if you use a large number of test station computers because each test station computer can retrieve the most recently modified files from a central location. Test station computers use local copies of files from the SCC server, ensuring operation during a network outage. Submitting modified files does not affect executing test systems because, again, test station computers receive changes when requested. You can also synchronize to a previous version of the test system if you require it. You can install files in Teststand directories, such as the Teststand public or the Teststand application data config directory. You can create a deployment without having any specific knowledge of Microsoft Windows installer technology. You can also efficiently perform small updates to the deployment. The size of the files changed determines the size of the update, which does not require a large fixed overhead size. However, using an SCC system presents the following disadvantages. Designing an update process that manages network outages and avoids race conditions requires additional development time. However, using an SCC system to develop an update process typically is more straightforward than developing an update process based on a network drive. The test station computer site also requires more network infrastructure, such as IT resources for maintenance, SCC administration resources, and the required hardware to make all of this happen. Copying files to a test station computer is also not sufficient for the test system to function correctly because you must also run installers ahead of time that install the Teststand runtime, any drivers or modules or third-party components you're using, as well as the SCC client application. And because the source code control system stores a copy of all versions of all files in the test system, the disk space can become very large very fast as well. The next strategy to consider is the Teststand deployment utility. It can be burdensome to try to manually manage hundreds, even thousands of files required by your test system. The Teststand deployment utility is beneficial in that it makes it easier to add all of the components to the deployment and configure where they will be installed on the target machines. It handles code module dependencies a lot easier because it's able to detect what the static dependencies are of your code. It also supports patch installers, making incremental updates to your existing deployments much easier than having to rebuild, redo, relink everything. These processes enable you to deploy a test station that is outside of a shared network, does not have network access, or does not have access to source code control. It also ships with Teststand and is part of the Teststand sequence editor package. The Teststand deployment utility can be used for creating an image, which is an image of your deployable system, so it's useful for testing on the development machine what your deployment will look like. It'll create the hierarchy of your sequence files, code modules, code module dependencies, user interfaces, and maybe any other files that you have included on your development machine so you can see what it looks like before you deploy it. It's also able to create an installer, which generates an MSI Windows installer that contains the image files that can be installed on a target machine. This also has the ability to include drivers and runtime installers, including the Teststand runtime engine. Therefore, it must be used if you want to include the Teststand engine or additional NI software components in your installer as a part of your deployment. It also offers you the ability to distribute packages. You can create a package similar to an installer and use NI Package Manager to install and run that on a deployment machine. It can create a single package or a package installer. When creating a deployment using the Teststand deployment utility, you'll have to select the output type on the very first tab. The options are to create a deployable image, so this is just creating the image that we discussed before, where the files are moved to the specified image directory on your System Source tab. You have the ability to create an MSI-based installer, so in addition to creating your deployable image, this also creates an installer for you to distribute that image, or you can create a package-based distribution. This will create either a single package where the files in the image directory are packed into a single NIPKG file. Dependencies you select are referenced by the package and must be installed on the deployment target in order to install the package. You can create a repository. This will create the main package, but all the other dependent packages are also included in the deployment. Then you can generate a feed that references this repository, which will include all your necessary packages for deployment. Or you can create a package installer. So in addition to creating the main package, all your dependent packages will be included in the deployment, and a standalone installer will be generated, which you can use on your deployment machines to install all the necessary packages. It will also install NI Package Manager on the system if it is not present. Note that the package-based distribution option is only available for Teststand 64-bit versions. We can launch the Teststand deployment utility by going to Tools in the Sequence Editor, then choosing the option to deploy Teststand System. This will bring up the utility in a separate process from the Sequence Editor. On the first tab, we'll see that we are on the mode, and we'll be able to choose the output type as well as the deployment version here. If we navigate to System Source, we'll be able to choose whether we want to build a deployment from a workspace file or from a directory. For example, we can navigate to the Examples directory, pick the mobile device test, and just see what an output would look like. We'll include the subdirectories because the code modules live in there. And if we go into the distributed files, we'll be able to analyze and see everything in that folder that we would be deploying. So if we navigate, we'll see the VIs, everything in that folder that has been used. Installer options is grayed out because we do not have MSI-based installer checked as the output type. When we check that, the installer options is available. We can go into drivers and components and see all the drivers and all the NI components installed on that system. We also can go to build status, and here we'll get a list of all the steps that TSDU is taking when it starts to build. On the bottom, we have the options to load a .tsd file, a configuration that you have made for a previous deployment. You'll be able to save this one, create a new one, build it, and then when you're finished, you can just hit done and you can close out of this. To create a deployment strategy, you can use one, two, or all three approaches as a part of your deployment. For example, you might use source code control to manage updates to your test code, and then use TSDU to build a deployable image and save that image to a shared network drive. In this activity, you will consider the given scenarios and determine which deployment approach suits the situation the best. When you're finished, proceed to the next slide to review the possible answers. In the first scenario, we are creating a deployment for a machine that does not have any Teststand components installed. So you'll need things like the Teststand engine, potentially drivers, your test sequence, and its dependencies. The best approach here would be an installer. For the second scenario, where we have an existing test station that needs to be updated, so you'll need things like test sequences and dependencies, so any code modules, any test sequences that were updated. The best approach here is to create an image or possibly a patch with Teststand deployment utility. If you leave deployment and deployment testing as an afterthought and as the last task in your development process, you will undoubtedly encounter numerous unwanted problems during deployment. In this section, we will discuss how you can use deployment testing throughout your development to ensure successful deployment to end users. The first suggestion is to not wait until the end of development to try and build a deployment. Test at various points throughout your development by creating a deployment from what you already have. If you have LabVIEW code, you can test your code with the LabVIEW Runtime Engine adapter throughout development continuously. You can also test your code with the operator user interface. If it is an operator running this, do they have any issues? Does everything run as expected? And when you're finally ready to deploy the application to target computers, most aspects of this deployment have already been tested, so it makes creating your deployment that much easier. Here we see a sample process for feature testing. The first step is to ensure that the test system is in a good state before deploying to target computers. Testing this can be done by running the sequence analyzer on your Teststand files, which could potentially point out any issues. You can also perform a test run with an image of your deployment. The second step is to create the deployment. The third is to test that image on your development system. So once you've created that image from creating the deployment, use the files to see if everything runs successfully. Are all your paths configured correctly if they were relatively configured? Use the exact same constraints as you would on your deployment machine. And be cautious of settings that are being configured for the first time on your test system as well. The fourth step is to deploy your test system to a different computer. So this is where you do the final test of running your test system to ensure that the deployment works as expected, that things run completely and correctly. To ensure a successful deployment that includes LabVIEW code modules, first test out your code modules in your development system with the LabVIEW Runtime Engine adapter. This will catch any errors that you may have before you deploy it to your deployment machine. Another option is to consider using packed project libraries, a feature that is included in the Teststand deployment utility. This builds all of your required VIs into a single file, which reduces your inter-file dependencies. It also ensures that all your dependency files are not inadvertently changed and are included in your deployment. And it also adds a namespace to all your VIs, ensuring that there will be no VI naming conflicts and cross-linking. Use a single LabVIEW version when creating a test system to ensure that all LabVIEW code modules can be executed within a single runtime engine. The LabVIEW development system can execute VIs saved in a previous LabVIEW version. The LabVIEW runtime engine, however, cannot. If you're using multiple versions, mass compile all your VIs before deploying. Test the deployment image using the LabVIEW runtime engine to be sure that it works as expected. The LabVIEW runtime engine cannot recompile or upgrade VIs, so errors may occur with the runtime that did not occur with the LabVIEW development system. For more information on the deployment process, refer to the Deploy Teststand Systems topic in the NI Teststand Help. This provides highly detailed information on how to ensure a successful deployment. There is also the NI Teststand Shared Drive Deployment Reference Architecture white paper on ni.com, which offers additional information on deploying to a shared network drive strategy. Test sequences are often developed on one computer and then deployed to a different one. Once you develop a test program using Teststand, you must package the program so you can deploy it onto the appropriate system. In this exercise, you will use the Teststand deployment utility to package all the necessary files to deploy the test program. When you have finished with this exercise, proceed to the next slide. Under what circumstances would you want to create an installer instead of a deployment image? One scenario could be where you are deploying to a non-development station. Another could be wanting to include other software components like drivers, NI software, runtime engine, so on and so forth. Open-ended exercise 3. In this exercise, you'll create a sequence which uses batch synchronization to control the behavior of various message pop-ups. Refer to the Appendix B to complete this exercise. Review your solution against the provided solution for this open-ended exercise. How did you specify the number of sockets for the execution? A possible answer is to override the model options process model callback of the batch process model. In your version of the callback, you then use an expression to set the number of test sockets to 3. What batch synchronization setting did you use for each message pop-up step? For the sequential execution message, use the serial or one thread at a time batch synchronization setting. For the one socket only message, use the one thread only, first thread executes step, remaining thread skip batch. Review your solution against the provided solution for this open-ended exercise. How did you specify the number of sockets for the execution? A possible answer is to override the model options process model callback of the batch process model. In your version of the callback, you then use an expression to set the number of test sockets to 3. What batch synchronization setting did you use for each message pop-up step? For the sequential execution message, use the serial or one thread at a time batch synchronization setting. For the one socket only message, use the one thread only, first thread execute step, remaining thread skip batch synchronization setting. For the parallel executions message, use the parallel all threads enter simultaneously batch synchronization. In this lesson, we learned how to deploy a test sequence. To distribute a Teststand test system from one computer to another, you must first identify, collect, and then deploy all the components required by your Teststand test system to the correct locations on your target computer. Use a workspace to organize your development files and identify software dependencies. Depending on your needs, you can use some combination of the different approaches to deployment, such as a shared network drive, source code control, or the Teststand deployment utility. And lastly, you can use the Teststand deployment utility to create a deployable image, an installer, or a package distribution. Code modules with Teststand. In this Lesson 10, Using LabVIEW Code Modules with Teststand. In this lesson, we'll describe techniques for developing and deploying code modules that are specific to the LabVIEW development environment. In addition to the various ways to organize your code modules in Teststand, such as workspaces and sequence files, you can use LabVIEW-specific tools and techniques to organize the VIs that you create and use in a test system. Consider the test system requirements when you choose an organizational approach for your VIs. This approach can affect the maintenance, performance, and deployment of your test system. For additional information on these approaches as well as others, refer to the Organizing LabVIEW-based Teststand Systems topic in the NI Teststand Help. A LabVIEW project is a file that references VIs and files necessary for those VIs to run properly, as well as supplemental files such as documentation or related links. LabVIEW displays the components of a project in the Project Explorer window. Additionally, a project creates an application instance for VIs, which prevents conflicts with VIs outside the project. An application instance is very similar to the concept of a namespace. But for more information on this, please refer to the Working with Application Instances topic of the LabVIEW Help. When calling LabVIEW code modules, you can specify the application instance of the project by specifying the project itself in the project path of the step settings of the code module. When you reference the project, this will run the VI within the LabVIEW application instance of the project. In Teststand, navigate to the Module tab of the Step Settings pane, click the Browse button, and navigate to the LabVIEW project that contains the VI which you want to call. Click the VI Path drop-down menu to select that VI from the list of VIs that are now available to you from your specified project. When are times you should consider calling a VI within the context of its LabVIEW project? If you have a situation where multiple VIs share the same name, then it is good to call the project because this will keep them in separate application instances. For example, if you've developed a hardware abstraction layer that has initialized in all of these hardware abstraction layers, but they're for different hardware, such as one is for a scope, one is for a power supply, then call it within that project's application instance, and this will keep it more clear and will avoid loading conflicts. Another situation is if a VI depends on data or project dependencies, such as DACMX tasks or configuration files. In this demonstration, we will put the VIs used in the computer motherboard test sequence and call those VIs through a project in the sequence file. So first, we'll go into LabVIEW and hit File, New, and we'll open up an empty LabVIEW project and add our existing VIs to this empty project. So let's call this Computer Motherboard Test as well, and we'll save it in the directory of the other VIs that have already been created. So we'll go ahead and save this here, and then we can add existing files by right-clicking on my computer and hitting Add, and then we can just select all of the files we want to add, so all of our test VIs, and we'll go ahead and save it. And let's close out and now go to our sequence file and update it such that it calls all of the VIs from the project path. So we'll open up the computer motherboard test sequence. And you'll notice that for each step, there is no project specified. So let's go ahead and specify the project path by looking it up. So now you'll see that the VI is referencing its project. Now we can add the project for each step individually, or we can select multiple steps and update their project path simultaneously. And now that we've done that, each of these VIs are now referencing their project path. Using LabVIEW projects improves organization of code on disk. It also assists with managing large code modules with many sub-VIs and prevents cross-linking. In addition to the benefits listed above, consider the following caveats. You can't use LabVIEW global variables to share data with VIs outside of the project. They will be in different application instances, therefore they cannot communicate with each other through LabVIEW globals. If you call a VI from the project, you must use a project to call any other VIs that are also part of that project. Otherwise, the VIs can execute in multiple application instances and will not be able to share data with each other such as variables and hardware references. Something to consider for deployment is that when you do have multiple LabVIEW projects, Teststand Deployment utility will create a separate source to a LabVIEW packed project library is a LabVIEW project library that packages multiple LabVIEW-related files and dependencies into a single non-editable file, a .lvlibp, that you can call from other VIs. Refer to the Sharing Code with a LabVIEW Project Library white paper on ni.com for more information on the huge benefits of using a project library to share code. When creating a LabVIEW packed project library, the first step is to create a LabVIEW library that contains the files in your LabVIEW project. Then you create that packed project library's build specification, and then you go back and set the original library as the top-level packed project library file. The Teststand Deployment utility can create a single packed project library for each LabVIEW project used in the deployment. Use the Output VIs to a packed project library option to generate one PPL or packed project library per LabVIEW project used in the application. For example, if your sequence calls VIs from 3 different projects, this option would generate 3 different PPLs. You also have the option to generate a project that includes the build specifications used to create the packed project library. The option to include source for rebuilding packed project libraries will generate a project that you can use to rebuild your PPL independently of deployment builds. To choose the best approach for creating a LabVIEW PPL, consider these things. When you use LabVIEW, it is a faster build time, and it provides more control over the creation process. If you use the Teststand Deployment utility, this is convenient because it builds the packed project libraries at the same time as the rest of your system deployment. If you need the convenience, use Teststand Deployment utility. If you need the fast build times and higher level of controls, then use the LabVIEW development environment alongside the application builder. LabVIEW packed project libraries help you in the following ways. They're pre-compiled so the build time is shorter. They prevent linking errors by consolidating all dependencies into a single file. They create a separate namespace for all member VIs within different libraries. They also will prevent a lot of runtime engine errors because they are compiling the code. So when you deploy it, you are deploying built code rather than loose VIs. Consider the following caveats, however, when deciding whether or not to use PPLs. You can't directly edit the VIs inside of a PPL because it is the compiled version of your VI. And packed project libraries are also version specific. If you change the LabVIEW version on your test station, you will need to rebuild the packed project library for that new LabVIEW version. In this demonstration, we will create a LabVIEW packed project library for the computer motherboard test LabVIEW project with the Teststand deployment utility. We'll open up the computer motherboard test sequence from Lesson 4.1, and we'll launch the Teststand deployment utility to build a deployment out of this sequence file and its dependencies. So we'll create a deployable image only, and we'll navigate to system source and pick from a directory. We'll see that it'll point to the current sequence files directory from Lesson 4.1, and location of the deployable image is pointed out. We'll analyze the source files here, and we see all our VIs are showing up as dependencies. If we click on LabVIEW options, we'll have the ability to output VIs to packed project libraries, and we'll choose that option. We'll open up the options dialog to take a look at the other options it offers us. Let's rename this packed project library output to computer motherboard, and we'll deploy the source as well in case any debugging or any recompilation needs to be done. We'll hit OK and build this sequence file and its dependencies. And if you have a deployable image already created, it'll prompt you to replace the last build if it is not empty. And we see that the build is successful. Let's navigate back to the location of the deployable image to see our output. So we'll see the packed project library sources included with the lvproj that we used with the packed project library. If we open up the new sequence file from the deployable image, we'll see that the LabVIEW adapter has updated the source of the VIs to be from the LabVIEW packed project library that we created with the Teststand deployment utility. In this section, we will discuss the different ways in which you can call LabVIEW VIs from a Teststand step. There are several techniques for calling LabVIEW code modules from within Teststand. The first is a VI call, which is the standard way to call a LabVIEW code module, so just calling any .vi file. There's class member call, which calls VIs that have been defined as part of a LabVIEW class. There's property node call, which calls a LabVIEW property node directly from within Teststand, and then select an express VI option. And for all of these, we will talk about them more in depth in their respective sections. For the class member call option, call VIs that have been defined as part of a LabVIEW class. This option does support the dynamic dispatch feature of LabVIEW classes. For example, if you pass a more specific class reference to a class method call, Teststand will automatically call the implementation of the method in the more specific class. Suppose your test system needs to support testing two different models of solar panels. The solar panel test sequence steps will be the same for each model, but the implementation of the panel output voltage test will be different. Instead of creating different sequences for each model, you could implement the panel-related code as part of a panel class. Each child class then implements the code needed for the specific model. For more information on this topic, please see the Calling LabVIEW Class Member VIs Teststand Help topic. To learn more about implementing LabVIEW classes and dynamic dispatches, refer to the Object-Oriented Design and Programming LabVIEW course. Class member calls allow you to implement a sequence that dynamically dispatches based on the specific hardware used to test your unit under test. This approach is referred to as a hardware abstraction layer and can be useful in mitigating test hardware obsolescence. For example, you may want to develop a test sequence that chooses the appropriate DMM to use based on a user choice or a UUT requirement. In this demonstration, we'll open up the Calling Dynamic Dispatch VIs found in the Teststand public directory underneath Fundamentals, Calling Dynamic Dispatch VIs. This sequence demonstrates how you can use dynamic dispatch with LabVIEW classes from directly in a Teststand sequence to implement a hardware abstraction layer. With this approach, Teststand calls the implementation of each class VI corresponding to the class you select in the initialize dialog. We can see in the initialize step that the class path references DMM base DMM LV class, and this is how we pull the method that we'd want to call from the DMM class. Here, we use that DMM object reference and we pass that to all the other VIs as well. So we'll go ahead and run this with single pass so that you can see the initialize dialog. So we chose the base class to run here, and in the report we can see that the data was generated by the generic DMM base class. Now let's run this again, but let's run it with the child classes. So here we choose simulated DMM, we run that, and we can see that in the report, we point out that this was generated by the simulated class. Again, if we do the same thing, and this time choose the other class, you can see the same thing for the PCI 4070. So this can be an implementation for you for a hardware abstraction layer if you're going to be using many different types of DMMs and you want to abstract that away from the user so they don't have to worry about it and they can just use one sequence file for testing. In main sequence, we see that we have the reference to locals myDMM as an object reference underneath our locals, and that's passed between the initialize, read, and close steps. We see that all three steps use the class member call in order to call members of the generic DMM class. Then Teststand can dynamically select the implementation of the class VI, which matches the class reference that you chose in the dialog. To view the implementation of the LabVIEW classes, you can open up the project in the same directory that we found the sequence in. To learn more about HALs, or hardware abstraction layers, refer to the Mitigating Obsolescence with Hardware Abstraction Layers webcast on ni.com. There's also the option to call a LabVIEW property node directly from Teststand in order to configure properties such as LabVIEW I/O references or configure a property on a LabVIEW class. Note that this approach does require LabVIEW 2013 or later. At a high level, you can see what calling a property node looks like on this slide. So first, you'd want to insert an action step, then you'd configure that call type, and then you'd configure the settings for the property node once you've configured the call to be of a property node type. And then you can save the sequence file, and that property and that step will be saved for you. To find out more, refer to the Calling LabVIEW Property Nodes from Teststand topic in the NI Teststand help for details on how to execute each of these steps. LabVIEW Express VIs are VIs where the settings can be configured interactively through a dialog box. You can call an Express VI directly in Teststand by clicking the Select Express VI button on the Module tab of the Step Settings pane. This list in the pull-down menu populates with a list of all the available Express VIs. When you select an Express VI, the configuration dialog for that Express VI will appear. Once you configure the Express VI and click OK, the VI parameters table will populate with the name and settings for each parameter needed for that Express VI. In Exercise 10.1, you will create a project for the solar panel test code modules and use the Teststand deployment utility to build them into a packed project library. When should you create the LabVIEW project that you use to organize your code modules? To maximize the benefits of using a LabVIEW project, you should create it at the beginning of your code module development and incorporate that into your code module development process. When you deploy your test system, there are a variety of tools and techniques that can be used to verify that the deployment was successful. When your test system includes LabVIEW VIs, there are additional techniques that can be used to test and debug the LabVIEW code modules. During test system development, it is common to configure the LabVIEW adapter to run VIs using the LabVIEW development system. Configuring the adapter to use the development system simplifies editing and debugging during development. However, the production test system that you deploy the code may not have LabVIEW installed. In this case, you will need to deploy the LabVIEW runtime engine. Note that just because a VI runs successfully with the LabVIEW development system, this does not ensure success when running it with the LabVIEW runtime engine. During development, you should periodically change the LabVIEW adapter configuration to use the LabVIEW runtime engine so that you can verify that the code will execute properly when deployed to a production test system. When executing code using the LabVIEW runtime engine, the entire VI hierarchy for that module must be the same LabVIEW version. The LabVIEW runtime engine cannot handle code modules with dependencies that are saved in different LabVIEW versions. The LabVIEW runtime engine, unlike the LabVIEW development environment, which is launched in a separate process, does not have the ability to recompile your code. So when calling your top-level VI, the top-level VI and its dependencies must all be in the same version for the LabVIEW runtime engine to be able to successfully load and run this VI within the Teststand process. Version-independent runtime engine support was introduced in LabVIEW 2017. And this allows LabVIEW runtimes to load source files such as VIs and projects, build outputs such as packed project libraries, DLLs, and executables that were saved or built in an older version of LabVIEW. Enabling this feature in Teststand reduces the number of LabVIEW runtime engines that would be loaded into the Teststand process to execute LabVIEW code modules. But note that you can enable the Enable Version-Independent Runtime Engine option if your machine is LabVIEW or LabVIEW Runtime Engine version 2017 or later. Changes made to this option do not take effect until you restart the Teststand application. In order to have the top-level VI and all of its dependencies in the same version, you can mass compile your LabVIEW code prior to deployment so that all of the VIs will execute using the same version of the LabVIEW runtime engine. To mass compile your VIs from the LabVIEW development environment, select Tools, Advanced, Mass Compile, and then you can mass compile a directory. Otherwise, if you are using a project, you can right-click on the project heading and choose Mass Compile. When using the Teststand deployment utility to deploy a test system that includes LabVIEW VIs, Teststand will create a temporary project in the Windows temp directory as the build process takes place. From this temporary project, you can use built-in LabVIEW tools to investigate any LabVIEW-related deployment problems that you may encounter. For example, you can use this project to identify any missing dependencies. You can use the Find Callers tool to review the VIs that call the specified VI as a sub-VI. You can use the Find Sub-VIs to review the sub-VIs that the specified VI calls. This is to ensure that you are calling the proper VI that you intend to deploy. This project does require the Teststand deployment utility to be open because once you close the Teststand deployment project, it will also remove the project from the temporary directory. Lesson Summary. Using LabVIEW code modules with Teststand. In this lesson, we learned how to use LabVIEW projects to organize your code modules. Call those code modules through the LabVIEW project to prevent cross-linking. We also learned how to use packed project libraries to shorten the build time of your test system and to further organize your files for deployment. When appropriate, call LabVIEW class method VIs, property nodes, and express VIs directly from Teststand. And finally, verify that your test code will execute through the LabVIEW runtime engine throughout the development process.